Hello student, last class we have discussed what is Biot-Savart law and its application, clear, and direction of magnetic field. How to find direction of magnetic field, what is the magnetic field strength by using Biot-Savart law. So in this session or in this class we will start the important law to determination of magnetic field, that is known as Ampere's circuital law. This is important law for calculation of magnetic field and this law is easy to calculate magnetic field. Clear? So according to this law, this is statement of, now we have to write the statement of Ampere's circuital law. So according to this law, the line integral of magnetic field, around a closed path or around a closed loop in free space is equal to mu naught times, or absolute permeability times is equal to mu naught times the total current within the closed path or closed loop. Clear? This is the statement of Ampere's circuital law. So according to this statement, that is the line integral of a magnetic field around a closed path or any closed loop, or any closed path in free space is equal to mu naught times the total current within the closed loop. So this is the statement of Ampere's circuital law and its mathematical formula, and it's B dot dl over closed integral, which is equal to mu naught times total current within the loop or inside the loop. So this is the mathematical statement or mathematical form of Ampere's circuital law, and this integral is known as line integral. We know from Gauss law in electrostatic. What is Gauss law? According to Gauss law, the surface integral, that means E dot dA, electric field area vector over a surface integral, and Gauss law, which deals with the surface integral, which is equal to Q inside by epsilon naught. Clear? This is Gauss law in electrostatic, or this is Ampere's circuital law in magnetism case. Clear? So this line integral and the circle indicate for closed path. So this is line integral, and the Ampere's circuital law deals with the length, but the Gauss law which deals with the surface. This is the difference between Ampere's circuital law and Gauss law. Here mu naught. What is mu naught? Mu naught means absolute permeability in free space, and I inside means total current within the loop or total current within the path. Clear? So this is the statement of Ampere's circuital law. But here, what is B and what is IE? First we have to know what is B and what is IE. That means B dot dl over a closed line integral, which is equal to mu naught times total current within the loop, that means inside or enclosed. So what is B? Suppose we have, there is two type of current I1 and another current, that is I2, and this indicates that the current which is inward direction and perpendicular to this plane, and this point, the point and circle indicate that the current which is coming outward, that means this is the flow of current in outward direction, and this cross indicates this is the flow of current in inward direction. Clear? Now first we have to find what is B and what is I inside. Clear? So suppose there is another current which is flowing inward direction and it can be represented, that is I3. Clear? But this law is only applicable for a closed path. So we have to make first a closed path. Suppose this is our closed path and our closed loop. This is closed path or closed loop, and this closed path is known as Ampere's loop. Ampere's law. Clear? Okay. Now look at the diagram. There is current I1, I2, I3. This is inward direction, outward direction, and inward direction. Clear? So first we have to know what is the value of B. B means B net. What is B net? B net means this is the net magnetic field. This B which indicates the net magnetic field due to all the current. That means within the closed loop and outside the closed loop. This B which is net magnetic field effect due to within the closed loop, that means I1, I2, I3. Clear? So magnetic field, this is the total magnetic field due to I1 current, I2 current, I3 current. That means the current which is within the loop and current which is outside the loop. Clear? So this is the effect of magnetic field. Now we will come what is I inside. I inside means this is closed loop and this loop is known as Ampere's law. First we have to find a direction, because there is two type of current which coming inward direction and which is coming outward direction. Clear? Suppose this is the direction of Ampere's law. Ampere's law, because we have to choose the direction to determine current direction. Clear? So in this case this is the direction of Ampere's law, and here current flowing inward direction and here current flowing outward direction. Clear? So this is the direction of Amperean law. Now we have to use the right hand palm, that is the if we call the finger, or if we call the finger along the direction of Amperean law, then the thumb indicate the direction of net current. Clear? So in this case this current is inward direction and this current which is coming outward direction. So net current according to this law, net current which is outward direction, because this is Amperean law, this is the direction of Amperean law, so this is the direction of flow of current. So this current which is coming outward and this current which is coming inward. So according to this direction of Amperean law, we can write the net current or I enclosed or I inside or I within the loop, which is equal to I2 minus I1, because I2 is along the flow of current I2 which is outward direction, but the flow of current I1 which is inward direction. Clear? So this is I enclosed. If we change the direction, suppose, because the direction of Amperean law depends on you can take any direction. Suppose this is the direction of Amperean law and this is the direction of Amperean law. Now we have to use here also right hand thumb rule, and this is the call the fingers. If we call the finger which indicate the direction of Amperean law and the thumb indicate the direction of flow of current, that means net current which is inward direction. So from this diagram or from this direction of Amperean law, we can write the net current, that means I enclosed or I inside which is equal to I inside means which is inward direction. That means the net current which is inward direction, because here inward direction is I1. So net current can be write I1 minus I2. Clear? So from this relation we can write the ampere cycle, that is V dot dl over line integral, which is equal to mu naught times I inside. So I inside means I1 minus I2. Clear? So this is all about how to use the ampere cycle law. Clear? Now we have to prove this law by using an infinite long state conductor. Clear? So we have to prove this law, proof of this law from infinite long state conductor. Suppose we have a infinite long state conductor. Suppose this is infinite long state conductor. Clear? And this point is P, where at a distance r. Suppose this distance r. This is perpendicular distance for infinite conductor. We know from Biot-Savart law, the magnetic field due to a long state conductor at point P or at a distance r can be write, that is B equal to mu naught by 4 pi 2 I by d. D means r. From Biot-Savart law. Clear? Or we can write 2 to the 4. Then the relation can be write mu naught I by 2 pi r. Equation number 1. Because by using Biot-Savart law, the total magnetic field due to a long state conductor or infinite long state conductor, this is minus infinite and this point is plus infinite, and at point P the magnetic field strength equal to mu naught I by 2 pi r. Clear? But here we have to prove ampere cycle law from this relation. Clear? Okay. Now second thing, suppose we have to draw here a Amperian loop. What is Amperian loop? Amperian loop is like a closed path or close. We have to draw a closed path with the closed path which passing through point P. Clear? Okay. So this distance is r. Now draw a Amperian loop. This is Amperian loop or closed loop. This is the direction of flow of current, which is outward direction. If we imagine, if we see top view of the current, because this is the direction of flow of current, if we this is the direction of flow of current, if we imagine or if we see from the top of view, then we can write a top view or we can draw a top view diagram. Top view. Then this is the direction of flow of current. This is the direction of, because the current which is moving outward is the top view. The top view. So that is the direction of flow of current I. Clear? We know that if this is the direction of flow of current, by using right hand thumb rule, and the thumb indicate the direction of flow of current, and if you call the finger indicate the direction of magnetic field lines, and the magnetic field lines form a circular ring and concentric circular ring, that means around the conductor. Clear? So this is the direction of flow of current which is coming outward. If we use your right hand thumb rule, then the thumb indicate the direction of flow of current. Clear? And if we call the finger, this is the direction of flow of current. If we call the finger, then this is the direction of magnetic field. Clear? This is the direction of magnetic field in this way. And the magnetic field lines are concentric circular ring. Clear? Now we have to draw a Amperian loop through the radius r. Suppose this is the Amperian loop over the magnetic field lines. This is the Amperian law, and this distance is r, and it's the direction of Amperian law also. Clear? And this is the direction of magnetic field B, and it's the direction of Amperian law. Clear? So if we choose a small element dl, what is dl element? We have to choose the length of the direction of dl element is along the direction of Amperian law, and this is the direction of magnetic field also here. So from this relation or from Ampere's cycle law, it is LHS left hand side, that is B dot dl over a line integral, which can be write, that is B dot dl A dot B, that means A B magnitude dl magnitude cos theta. So B dl cos theta over line integral or closed integral. So what is theta? Here theta is angle between, theta is the angle between magnetic field and length element or dl. Here small length dl. So in this case, it's the direction of dl element and it's the direction of magnetic field. And the Amperian law, which indicate that the symmetry of the law. Symmetry means if you choose this point here, magnetic field strength, and if you choose another point here, another point here, all the 4 points magnetic field strength equal, and the direction of magnetic field in this direction, and this point the direction of magnetic field in this direction, and this point the direction of magnetic field in this direction. Clear? So this is the direction of magnetic field at 4 points, and we chose also this is the direction of Amperian law. So if we choose another point here, then this is the direction of also dl element. Here this is the direction of magnetic field and this is the direction of dl. So theta here is 0 degree, because dl vector and b vector along one line, so theta equal to 0. Here also theta equal to 0 degree, and here also if we choose another element, then this is the direction of magnetic field and this is the direction of dl element. So here theta equal to 0 degree, and here theta equal to 0 degree. Clear? So Ampere's cycle law gives the symmetry. Symmetry means each point magnetic field is same, each point or this point magnetic field strength is same, and this point theta also same. This is the importance of Ampere's cycle law, and which gives the symmetry. So if we use this relation, then this point theta equal to 0, and this point also theta equal to 0, and from this point theta equal to 0, and this point theta equal to 0. Clear? So B dot dl cos theta we can write, that is close integral, B dl cos 0 degree, and its value theta B dl, because the value of cos 0 degree equal to 1, because the value of cos 0 degree equal to 1. Now we can write, because B is constant quantity at 4 point the magnetic field strength is constant, so we can write, that is B dot dl over a line integral which is equal to B, this is constant quantity, so we can take it out from the integration. So dl, and the integration of dl, that is B integration dl, this is dl element, dl. So total length of the circular law, which is 0 to 2 pi r, 0 to 2 pi r, because r with the radius of the Amperian law. Clear? So then B, the integration of dl, which is equal to L, the lower limit 0, upper limit 2 pi r. If we use the upper limit and lower limit, then the other equation turn to be, that is B 2 pi r minus 0, which is equal to B 2 pi r. This is equation 2. Now we have to substitute the equation 1 in equation 2. Now putting the value of B from equation 1 in equation 2. Now we have to use the value of B from equation 1 in equation 2. So in equation 2, that is B dot dl over a line integral which is equal to 2 pi r into B, and if we use the value, that is 2 pi r into B. What is B from equation 1? That is mu naught times I divided by 2 pi small r. Here 2 pi r cancel, so remaining term which is equal to mu naught times I. And what is I? I means total current which is coming outward direction within the amperian loop. Clear? And this is RHS. So this Ampere-Sartel law can be proved by using Biot-Savart law, the magnetic field Biot-Savart law, in case of there is a infinite long state conductor. Clear? Application of Ampere-Sartel law. So first application, magnetic field strength due to a infinite long cylindrical current carrying conductor or current carrying wire which is solid. So this is the model of a cylindrical wire and which is solid, and this is the direction of flow of current. This is the cylinder which is infinite, and here this is the direction of flow of current. This is the direction of flow of current. Here due to solid cylinder, total current flowing through the surface and total current also flowing through within the cylinder. Here this is solid element, and this is the axis of the cylinder, and which is infinite cylinder. This is plus infinite, and here infinite. This is minus infinite, and this is the axis of a solid cylinder. Clear? We have to find magnetic field strength at point A, which is outside the cylinder. And second thing, we have to find magnetic field on the surface of the cylinder. And third point, we have to find magnetic field within the surface or within the cylinder. Clear? So we have to find magnetic field 3 point: outside the surface, on the surface, within the surface. Clear? So first we will go for magnetic field outside, for outside point. Outside point P. That means here R which is greater than R. What is R? This is axis where we have to find magnetic field strength. This is the distance. Clear? But capital R which indicate the radius of the cylinder. So this is point A, and here we have to find magnetic field strength at point A at a distance r from axis of the cylinder, and this is the direction of current which is I flowing through the cylinder. This is solid cylinder. Clear? Now first we have to draw a amperian loop, and imagine that this is the direction of flow of current. If this is the direction of flow of current, if this is the direction of flow of current, then it's the direction of magnetic field. This is the direction of magnetic field in this way. This is the magnetic lines in this way. So we have to choose a amperian loop which is symmetry of the magnetic lines. Suppose we have choose a amperian loop in this way, and this amperian loop which is passing through point A. So first we have to draw a amperian loop, and this is the amperian loop. Clear? This is amperian loop. Suppose this point, if this is the direction of current, then this is the direction of magnetic field. So magnetic field at this point which is inward direction, and current element or dl element, suppose we choose a length element dl which is also inward direction. Clear? And here theta equal to 0 degree. And if we choose another point here, then this point magnetic field which is outer direction and dl length element which is outer direction, and here also theta equal to 0 degree. That means theta each and every point on the, this is Amperian loop, theta each and every point on the Amperian loop is constant, and magnetic field also on the Amperian loop each and every point is constant, because this length is r, and this length is r, and this length also r, and this length also r, and this length also r. Clear? So according to Ampere's sector law, we can write that is B dot dl over closed integral which is equal to mu enclosed or mu naught times total current enclosed the Amperian loop. This is Amperian loop, so total current within the loop which is I. So we can write that is mu naught times I. Next, B dot dl which is equal to B dl cos theta, but theta here 0 degree, each and every point on the surface of on the Amperian loop. So you can write B dl cos 0, that is B is constant quantity, so you can take it is dl which is equal to mu naught I. And what is dl? 0 to 2 pi r, because this is r and the circumference which is equal to 2 pi r. So B into the integration of dl, that is L 0 to 2 pi r which is equal to mu naught I. And if we use upper limit first, then this quantity or this relation turn to B into, this is 2 pi r, so you can write 2 pi r equal to mu naught I. This is mu naught I. So B equal to mu naught I by B equal to mu naught I by 2 pi r. Clear? Just like a infinite long state conductor, at this point the magnetic field B equal to mu naught I by 2 pi r. This is the outside point, and in this point the magnetic field which is inner direction, and this one the magnetic field which is outer direction. Clear? This is all about how to find magnetic field strength for a solid cylinder at outside point. Now we will go on the surface of a cylindrical coil. Clear? Now we have to find magnetic field on the surface of a cylinder. This is the surface of a cylinder at point B. So second point, on the surface, that is point B, we have to find magnetic field at point B on the surface of cylinder. Clear? So in this case we have to draw a imaginary Amperian loop which is over the and which is coincide with the surface of the cylinder. Clear? And this point, this distance is r. As we know, for the outside point, the magnetic field, that is B equal to mu naught I by 2 pi r. But here it is r equal to capital R. So magnetic field at point B or on the surface of a cylinder, rectangular cylinder, it is B equal to mu naught I by 2 pi. Here small r and this is capital R. Clear? This is outside point. This is for outside. This is on the surface which is equal to mu naught I by 2 pi r. Clear? Now we have to find magnetic field strength inside the surface or inside the cylinder. Suppose there is a point A, B and point C. We have to find magnetic field at point C, the point C which is within the cylinder. Clear? Now this distance is r. This distance is r. Suppose small r. Clear? Because the distance always measured from its axis. So first we have to draw a Amperian loop, and this is Amperian loop. First we have to draw a Amperian loop of radius r. Last point or third point inside the cylinder or at point C. We have to find magnetic field strength at point C by using Ampere's sector law. and the point C which is within the surface, that means inside the cylindrical surface. Clear? First we have to draw a Amperian loop which is passing through the point C with radius small r. That means here small r which is less than capital R. Clear? In this point. So now we have to use Ampere-Central law, that is B dot dl over closed integral equal to mu naught times I enclosed. What is I enclosed? I enclosed means total current within the Amperian loop. Here total current within the Amperian loop, which is not, this is total current I, total surface for the inside, and this is total I within the surface, but this is point C which is inside. So total current I which is not flowing within the surface. This is the current which is within the surface, and this current which is, imagine I dash. I dash which is not equal to I current flowing through total area, but total area equal to, which is equal to pi r square. But this I dash current which is flowing through this area, and this area, this is small area, and this area small r, radius small r, so its area, that is a dash, which is equal to pi small r square. This I current flowing through this area pi r square, but this I dash current which is flowing through this pi r square. So first we have to find this I dash current which is in terms of I, because which is I enclosed, that means within the Amperian loop the current flowing through I dash which is this direction. This is the direction of Amperian loop. Clear? So if we choose here a small point, then this is the direction of magnetic field and this is the direction of Amperian loop. So each and every point theta is same and theta equal to 0 degree, because the direction of magnetic field and the direction of length dl element is 0 degree. So you can use, that is B dot dl which is equal to B dl cos 0 degree close integral equal to mu naught into I enclosed, equation 1. First we have to find what is I enclosed. So here I enclosed equal to I dash. I enclosed equal to I dash, because this is Gaussian, Amperian law and current flowing through the Ampere law which is I dash. First we have to find the value of I dash. Now this is total surface area, and for total surface area current flowing through I. That means for total area of cross section, that is total area of cross section pi r square, and current flowing through the cross section, that is I. Total cross sectional area current flowing through I, that is for unit cross sectional area, for unit cross sectional area which is equal to I by pi r square, and this quantity is known as current density. You know what is current density? That means current flowing through unit area. That means 1 unit area current flowing through I by pi r square. For 2 unit area, current, that is I by pi r square into 2. For 3 unit area, I by pi r square into 3. Similarly for pi r square, because this area which is small r, which is radius small r, and this area pi r square. So for pi r square area, cross sectional area, the current flowing through this cross sectional area which is equal to I by pi r square into pi r square. Clear? So current, and this can be right, that is I dash. So I dash is the current which is flowing within the Amperian loop of radius small r, that is pi r square. So I dash equal to I by pi r square into pi r square. 1 pi cancel, so we can write that is pi r square, sorry, I small r square divided by capital R square. This is the current which flowing through the Gaussian surface, the Amperian surface, and the surface which is inside the cylinder. Clear? So now we have to use this relation here. Idea is equal to I by pi r square, 1 pi cancel, so I r square by I r square. So if we use this relation here, we can write which is equal to mu naught into I dash equal to I r square by capital R square, and b dl cos theta cos 0 equal to 1, this value equal to 1, and b is constant quantity, so we can write dl which is 0 to 2 pi small r, which is 0 to 2 pi small r, that is 2 pi r. So b into element L, then 0 to 2 pi r equal to mu naught times I r square by I r square, and b into 2 pi r which is equal to mu naught I r square by capital R square. Clear? Now the above relation turn to b which is equal to b, that is b equal to mu naught by 2 pi r into I r square, so I r square by capital R square. Clear? So 1 r cancel, so b equal to mu naught I by 2 pi, mu naught I by 2 pi, mu naught I by 2 pi by r square into r. This is the magnetic field strength within the surface, that means inside the surface. This is inside the surface. Clear? So from this relation we conclude that is magnetic field for outside point is b equal to mu naught I by 2 pi r. Clear? b equal to mu naught I by 2 pi r on the surface of the cylinder, that is b equal to mu naught I by 2 pi, and this r will be capital R. That means outside point, that is r equal to r, but here on the surface r equal to r, and inside point, inside within the surface or inside, that is r which is less than capital R, in this point b equal to mu naught I which is divided by pi r square into r. Clear? From this relation here, that is b, and this is r, this is constant, mu naught constant, I constant, 2 constant, pi constant, but r is variable, because if this is cylindrical element, this is axis, then this point is r, this point a, and this point is this point b, then r also decrease. So here r is variable, so we can write b inversely proportional to r. That means if we decrease the length of the, if we decrease this length, then magnetic field also increase. If we decrease this length, then magnetic field strength increase. If we increase this length, then magnetic field decrease. But this point, the magnetic field is constant, because mu constant, I constant, 2 constant, pi constant, r constant. So this point magnetic field is constant. This point, and this point, total circumference, the magnetic field which is constant quantity. Clear? This is constant quantity, and this point magnetic field strength is maximum. Clear? On the surface of a cylinder. Come to this last point is constant. This is constant quantity. 2 pi r square also constant quantity for this relation, but here small r means within the surface, and this distance r for last case. So in this case b is directly proportional to r. What does it mean? If this is axis and this point is within the surface, if If we take this point on the axis, then R will be 0. If this point take on the axis, then R will be 0. So magnetic field strength on the axis of a cylinder will be 0. If we increase this length, then magnetic field also increase, because B is directly proportional to R. If we increase length, then magnetic field should increase. If we increase and come to and reaches the point on the surface, then magnetic field which is equal to mu naught I by 2 pi R, and which is maximum. That means if we come from axis to on the surface, then magnetic field increase. But after the surface, if we come after the surface, that means outside surface, then magnetic field decrease. So if we draw a graph by using this relation, then the graph will be like this. Graph, this is distance and this is magnetic field strength. Graph versus magnetic field versus R, distance graph. Clear? Now look at this relation, and first inside point. Clear? B equal to B is directly proportional to R. That means if we take this is cylinder, this is axis, inside point, this is R, this is on the R surface, and this point is R, outside point. Clear? But inside the point, inside the surface, magnetic field which is directly proportional to R up to outside surface. That means here magnetic field increase and stop. That means here constant. That means magnetic field increase from the axis of the cylinder to on the surface. Then magnetic field decrease. So magnetic field increase, that is B directly proportional to I. So B directly proportional to R, because here R and this point, it is R equal to capital R. That is, this is inside, and this point is known as on the surface. Clear? Because on the surface, the strength of magnetic field which is maximum. This is on the surface, where R small r equal to capital R. But if we come from the outside point, then magnetic field is inversely proportional. Then this is like this. This is outside point where B is inversely proportional to R. This is graph and graphical representation of magnetic field strength due to a solid cylinder. For hollow cylinder, suppose we have a hollow cylinder which is infinite and current flowing through the surface, not within, current flowing over the surface which is I. That means this is direction of current and current flowing through over the surface of a hollow cylinder. Clear? There is also 3 point A which is outside point, first point which is outside, that means R which is greater than R, and this point R, this is the radius of the cylinder, hollow cylinder, and this point we have to find magnetic field. Then we have to first draw a imaginary ampere loop, and total current within the loop which is I. The same thing for solid, that is B equal to mu naught I by 2 pi R. Here also, that is B is inversely proportional to R. B is inversely proportional to 1 by R. Clear? Same thing as we discussed previous, that is for a solid cylinder, similar case. So next on the surface of cylinder, that means on the surface, if you draw a imaginary, then this is on the surface, if you draw a imaginary ampere loop, then total current flowing, this is within the surface, then total current flowing over the surface which is current I, and in this case the B equal, we can write B equal to mu naught I by 2 pi capital R. Same thing as solid case, but inside the surface, inside point, this is outside on the surface which is R equal to R, but inside R. Suppose we have to find magnetic field strength at this point. Suppose this point C, which is at a distance r within the hollow cylinder. Clear? This is a hollow cylinder and this is the circumference or area, or this is the surface. In this case, for hollow cylinder, total current flowing through over the surface. This case and this direction, this is the direction of flowing of current. But inside the hollow cylindrical conductor, there is no current because total current flowing over the surface. If we choose a point here within the hollow cylinder, then first we have to draw a amperian loop. This is amperian loop and this is the radius, which is equal to pi r square. Clear? But within this area there is no current because total current which is flowing over the surface, but inside the surface there is no current. That means if we use Ampere's law, then we can write for this case, that is B dot dl over closed integral, that is mu naught times I enclosed. I enclosed means here there is no current because this point we see which is inside the hollow cylinder, so I equal to 0. If I equal to 0, then magnetic field inside the surface equal to 0, so B equal to 0. That means magnetic field inside the surface of a hollow infinite current carrying cylinder, which is equal to 0. Here there is 3 point also, point 1, point 2 and point 3. Inside the hollow cylinder, magnetic field strength is 0, but outside the point mu naught I by 2 pi r, which is equal to solid cylinder. But if this is on the surface, this is outside point, which is equal to mu naught I by 2 pi r, which is equal to the solid cylinder. If you draw a graph, magnetic field versus distance, then magnetic field versus r, this is x-axis and y-axis. If we choose the distance along x-axis and along y-axis, we have to take magnetic field. Clear? But this is the axis. On the axis, magnetic field is 0. If we increase the length from axis up to surface of the hollow cylinder, then magnetic field strength also 0. That means here magnetic field, if we increase the distance up to r equal to r, if we increase the distance up to here r equal to r, then magnetic field strength is 0. This is the magnetic field strength. Here magnetic field strength is 0. Next, then if we increase the distance after the surface of the hollow cylinder, then magnetic field strength is decreased. That means B is inversely proportional because B is inversely proportional to 1 by r. This is outside point. B is constant quantity. B is constant or maximum on surface and B equal to 0 inside. So if we take another point which is outside is A point, then magnetic field strength decrease. This is the graph. Clear? This is outside. This point is on the surface and this point inside. Clear? And this point magnetic field is maximum. So from this graph we conclude that magnetic field strength within a hollow cylindrical current carrying wire is 0. Here magnetic field is equal to 0, but on the surface magnetic field strength is maximum, which is equal to the magnetic field strength like solid cylinder, but outside the surface magnetic field strength is decreasing. Clear? This is all about how to calculate magnetic field strength for a hollow and solid infinite long state conductor.